Hello, everyone. I will be talking about structural ceramics, and we all know they are awesome. They can have high wear resistance, high temperature resistance, and they are strong, but they contain a lot of flaws, pores, inclusions, and whatever. And they are also very brittle. That means when the crack initiates in these ceramic components, the failure can be catastrophic. So we want to avoid that and increase the resistance and reliability. And in the first lecture, at the end, you proposed we can also use the residual stresses by combining materials that have different thermal expansion coefficients. And that's exactly what we do. And we want to use this material in applications where it comes to the thermal shock. And thermal shock, this is a situation where the surface is giving the heat to the cooling medium faster than the inside of the specimen is able to equalize the temperature. Therefore, you have gradient of temperature and thermal stresses. And if they are too large, your specimen will break. On the left side, you see bores from silicium nitride. They have pre-cracked notches. And on the right side, that's alumina and zirconia composite, which I will be simulating now. We have multiple methods how we can assess this approach with residual stresses. The classical is linear elastic fracture mechanics. But why it's not so useful? Because we usually have millions of defects. We don't know the location. We cannot characterize the specimen properly. So sometimes it's useful, but not always. The classical approach would be Weibull statistics, but it has some assumptions which we violate in this case, and not in this case only, but also in the indentation. You violate this condition of constant stress along this defect size. And by the variational fracture mechanics, I mean the phase field. We also implemented that, and it's really awesome in predicting these crack patterns in the model because it can capture this branching and joining of cracks. But again, it's not really useful in predicting the critical temperature difference, which is our objective, to say at which temperature difference the component will crack. So we use something which is called finite fracture mechanics, and it's different from the classical one by the assumption of discrete crack growth. That assumption of Griffith is now thrown away, and we can use this assumption to even say, we don't know what the crack is. Maybe there is no crack, but we just compare the state without cracks and when the crack initiates and it's observable. And it's well-established approach. It exists for 20 years and it was used for indentation, coatings, and it's one of the approaches that really works. This approach uses something which is called coupled criterion. Usually you don't care about the strength and fracture toughness. You say one is depending on the other, but here they are really independent and you must fulfill both criteria simultaneously. You must have region in tension where the cracks are allowed to initiate. And at the same time, if you want to initiate this crack, you want to grow something, you need to fulfill the energy criterion. But we don't now use the energy release rate in the classical sense, which is the tangent of the potential energy, but we use the potential energy before the crack initiated and potential energy of the whole system, not at the crack tip after the crack initiates. So we 3D printed 4 specimens for our testing. It's rods from alumina and zirconia toughened alumina. And then we made 2 composites where we put some core and 4 micron thick shell. And the hypothesis is if we put on the surface compressive stresses, we will get higher temperature differences. If we have tensile residual stresses on the surface, naturally it will fail with less load. And we also exploit the observed phenomenon that the crack, when it initiates, and it has now geometry like these rods, it's not some disc or whatever, it will have uniform spacing. So then we can say it will be uniform, and we can use the some representative volume element and simulate some circumferential crack that goes around the rod, and we make this analysis much simpler. We could also try to simulate here some semi-elliptic crack, but it would not be that useful. So we do finite element analysis with these representative volume elements, and you can see on the left side that's monolithic alumina, and on the very left you have free surface. As you go up from the bottom, we follow time in milliseconds, and you can see after approximately 30 milliseconds, you reach the most critical conditions with respect to the strength, but that doesn't mean anything, because also with the increasing time, the boundary between the compressive region and the tensile region is changing. After much more time than, let's say, 10 seconds, the region is more deeper, where the cracks are under tension. Whereas in the composite, because we have compressive residual stresses on the surface, stresses on the surface are smaller, but at the same time, we are putting the core under tension. So you need to be careful and balance it out and try different designs. Now let's look at the incremental energy release rate. This is plotted at the same critical temperature. So we heated some sample to 400 degrees, throw it into water. And if it's monolithic alumina, you have some region depicted by the green color where cracks overcome the fracture toughness, but it's not the same case in the composite with compressive stresses, because there is no combination of time, temperature, or time or crack depth, which would allow you to grow cracks. But again, that's not sufficient. We need to always evaluate these conditions together. So let's look at it. The blue case is after 2 milliseconds. The stress, it's normalized by the strength and fracture toughness. So the strength is never reached, nowhere. The same goes for the energy release rate. It's almost overcoming the fracture toughness, but not yet. So let's go further. After 12 milliseconds, on the surface, you reach strength, but as you observe this is energy release rate. You have condition energetically that it doesn't matter how the crack depth, how long the crack is. It could be 10, 20 microns, and it will be already growing. And it's not improbable that you have this defect size in these specimens. So why didn't crack? Because the strength was not fulfilled yet. And after 22 milliseconds, you reach conditions where you have below the surface, this is surface, below the surface, you have approximately 40 microns of tensile region where you fulfill the strength. And at the same time, all cracks that are longer than 40 microns can propagate or initiate if they are not there. So this was for 3 discrete times. You can also do it at the same time for all time combinations and find some critical time and temperature defect size that would be observed. And if you do it for all temperature changes, we can plot this critical time, which fulfills the coupled criterion, and observe that there will be some critical temperature difference below which you will never observe cracking. And the positive message for us is when we use composite, we can gain, let's say, 100 degrees Celsius more resistance. In some cases, it could maybe be worthwhile. And if you play with the thickness of the shell, you make the shell thinner, your residual stresses go up. So you could play with this ratio to make it more resistant, or you can add more layers. We also use 3D printing approach to manufacture samples and compare predictions with the experiments. And I was surprised it matches the predictions well, because coupled criterion does not only provide the information when it cracks, but we could also do some sensitivity analysis. And we learned that, for example, indentation is very sensitive to the value of fracture toughness. For some reason, thermoshock is not that sensitive to fracture toughness, but it's really sensitive to the strength. So you need to be really careful with the surface when you design your components for thermal shock. And I will give you 4 takeaway points. So final fracture mechanics was proven in many cases it's very useful tool and it's simple to implement. Residual stresses can be viable strategy. So not only tailoring your microstructure with some elongated grains or let's say Gorilla Glass with the chemical strengthening, but residual stresses should work. And you should be careful. You should optimize your thickness such that you don't cause tensile stresses in the core to break the component. And thank you for your attention. You can also check the paper that is published with more detail. Thank you.